Okay, we are very happy to have Professor Vineet Goyal from Columbia. He's a professor at the IEO department at Columbia. He's a recipient of the NSF Career Award, the IBM Faculty Award, and Google Faculty Research Award. And he's interested in the design and analysis of algorithms, in particular robust data-driven algorithms for dynamic optimization problems. Today we're going to talk about assortment optimization problems in a different setting. He also spoke about assortment optimization a year back.
The motivation is the same,
yes,
but in a different setting. Thanks, Balu, for arranging this and the introduction. It's a pleasure to come back and again speak about assortment optimization. So today I'm going to talk about this problem under a distribution over permutations model, and in particular, a mixture of Mallows distribution over permutations. This joint work with my student Antoine Dasir and Shrikant Jagabatula, who's faculty at NYU Stern, and Dani Sagev, who's at Stanford Haifa. So just to set up the problem of assortment optimization, let me describe a concrete model. So think of n substitutable options. You have n substitutable options with exogenous prices P1 to Pn. Now, the preference of customers is specified by an ordered list over these substitutable options. So ordered list or a permutation. And a seller needs to decide what options to offer to the user with the goal of maximizing the expected revenue. Okay. Now, if a subset of options is offered to a user, the user would select the highest in his or her list. For instance, let's say I only offer options 1 and n. The first user, she has a preference list of 2, 3, 1, and then nothing. The empty set just says the user exits the system. So the first user would pick product 1, and the second user will go to would look for option 3, not there, so would exit the system. Okay, and in general, in a most general setting, preferences can be modeled as a distribution over permutations over these substitutable options. Okay.
Here you're not playing as prices, for example.
So the products are exogenous. All the features, including prices, are fixed. Therefore, the preferences of the population is fixed.
Yeah, I'm just curious if you also consider sometimes choice models that you can pick assortments and prices.
Exactly. So pricing is a more general problem than assortment because I can set the price to infinity, which implies that I'm not offering that product.
Okay, so you're saying that there's a particular subset of pricing. It's like a
This is a subset of pricing. Yes. So as you can imagine, this kind of problem would arise in many settings, in e-commerce, Amazon, product search, recommendation. So this arises in a variety of settings where the goal is to, from the seller's point of view, to maximize the revenue from the user. Now, I mentioned distribution over permutations. This is naively, this is a useless model. I cannot hope to estimate a non-parametric distribution over permutations. Okay. But really, I don't really need the distribution over permutation. I actually need the following object. That if S is the subset of options offered by the seller, what is the probability that a random user from the population clicks or selects J? Okay. And just mapping it back to the distribution over permutation, it is probability of all the permutations where J becomes the first offered item in their in that list. Okay, and concretely, the assortment optimization problem is finding the subset that maximizes this objective of maximizes the expected revenue from a random user in the population. And here I'm stating the unconstrained version, but you can have constraints like budget, like cardinality or budget constraints, or more general constraints over the assortment. Yes.
So is there a restriction that you have to include a null choice? Because otherwise, what keeps the seller from saying, the only car I sell is a Lexus, you got to buy it?
Great. So null choice is there for the users. It's not up to the seller to include or not include.
Okay.
Users have that choice. So if you do that, then what you sell for that, you will make high revenue, but your market share will be very low.
Okay, so S always includes null?
S always includes
No, actually,
null.
the null is not in S. S is a set of products. The null is in the set of preferences.
Oh,
So the preference is a permutation on the items plus null.
Oh, okay.
And the set, if they set intersection, the preference is nothing, then you go from null option with one byte.
Okay.
So like if you only offer Nexus, maybe if it's true that Nexus is one of the options, then what you said is correct. But if they hit null in their preference before that, then it's not.
So that's just a matter of semantics. You can think of S null being in S always, or null as an outside thing, and S is your subset. So
Go back to the first slide for 1 second.
okay.
You're saying because of the way that they define.
Yes.
So with the
Like,
probabilities that define
okay.
actually require null to be.
Okay. So so the two fundamental questions in this area are how to estimate a choice model, and then for that model how to solve the decision problem, that is the assortment problem. And estimating a choice model becomes particularly difficult because you don't observe the rankings of the users. You only observe their selections. You offer a subset of options, you observe the selections, not their rankings. So choosing what model to estimate, model selection becomes a difficult problem. And as with most problems, there are these fundamental trade-offs. You can choose a simple model that will be easy to estimate and solve the optimization problem, but may not be realistic in many settings. Or you can go to a more richer model, which models more closely the reality, but both estimation and optimization become hard. Okay. So in particular, this slide exactly shows these, explicitly shows these trade-offs. Multinomial logic model is the most widely used model in practice, which is essentially an extension of the logistic regression model. And this, so a multinomial logic is a n parameter model, one parameter for each product. And the choice probability is just proportional to that parameter corresponding to that product. Now you can also go into the feature space, and then this parameter vi is a function of the features of product I. Okay, and then you can even go to the feature dimension. Then the parameters are d instead of n. Okay, and still the choice probability is just proportional to this parameter vi. The estimation problem and optimization problem are both very simple in this model. In fact, you can solve the decision problem as an LP. Even when you have cardinality constraint, even with matroid constraint, this can be solved by an LP. But this is a very simplistic model in the sense that it satisfies this IIA property, which is independent of irrelevant alternatives, meaning the market share of product I and J is independent of what subset of options you show. The ratio of the market shares of I and J. That is independent of the rest of the products. Okay? That's very restrictive. Okay? Just think of a very simple setting. Let's say the population is divided half and half between red and blue product. Okay? No pun on the politics. So the V parameter for red and blue both will be 1. Now I introduce a red prime. That V also will come out to be 1, and this model would say 1/3, 1/3, 1/3. Whereas you actually should be, it should be 1/4, 1/4, and half. That is what that should happen. So this is very simplistic, doesn't capture real preferences. So more general models have been considered, in particular nested logit model, mixture of multinomial logit model. In fact, mixture of multinomial logit model is very general and can approximate almost any distribution over permutations. But then both of these generalization become harder to estimate and optimize over. In fact, for mixture of MNL model, the assortment problem is even the unconstrained version is independent set hard. Okay. So the motivation for this work actually arose from trying to address these trade-offs. And even if I ignore the computational complexity, which model should I select? Let's say I ignore the computational complexity of the decision problem, but which model should I pick? And that was the basic motivation of this work towards designing toward designing algorithm for the Mallows model. So we started out with looking at a very non-parametric approach, which is thinking about maximum entropy distribution over permutations. Okay. And it turned out that Mallows is a very special case of max entropy distribution, and that had not been addressed in the literature, and that's how this work really started.
So sorry, when you say maximum entropy, you mean that you want to observe your data and you want to pick the maximum entropy distribution to explain the data?
Exactly. So let's say you have pairwise comparison data.
Well, which pairwise? What is
so Qij is the fraction of people who prefer I to J.
Okay.
Let's say you have such data. And you have for some set of pairs, not even all.
So I have a
pairs.
graph saying what fraction of people prefer.
And now find the probability distribution over permutations that is consistent with these empirical observations.
I see. So you have
and maximizes the entropy.
But so if you consider triples, this might be inconsistent with this, right? Or is it?
What do you mean inconsistent?
So you're looking at the probabilities over pairs, which of the two elements is chosen.
Mm-hmm.
If you consider triples,
Mm-hmm.
what is the probability of each of these three elements? Is there a guarantee that this will necessarily be consistent with the permutations that you find as well, or not?
So arbitrarily, no. So if you give me arbitrary data, that will not be the case. But if you give me data which satisfies the following, that if you show me option S, set of options S1 and set of options S2, which is a superset of S1, then probability of each of the option in S1 can only go down.
Can you repeat that, sir?
So maybe I can use the board there. So if you have set of options S and P, then probability of J in S is only higher than probability of J in T.
So every permutation preference should
satisfy this.
And is this necessary and sufficient condition?
That is necessary, and you can find a feasible permutation, a distribution over permutation that would satisfy.
I see.
Okay, so that's
if you give me arbitrary data, then it's a problem.
I see. So that's the feasibility conditions for this.
Yes.
I see. There's not the data you have. The data you have is pairwise data.
Yes.
And for the pairwise data, is that clear? What's the feasibility conditions?
For pairwise data, any data would be feasible actually.
Can I have, like, for example, 99% prefer A than B, 99% prefer B than C.
Mm-hmm.
I cannot have 99% preferring C than A, for example.
Yeah.
There must be some sort of triangle inequality.
So what is the yes. So Yeah, I don't think we have a characterization. Okay. So yeah, so we don't have a characterization of what will lead to feasibility of the max entropy problem, but this is data. As long as data is coming out of preferences, then it will be
makes
feasible.
sense.
Okay. So before I go to describe our model, let me just mention this closely related work about a non-parametric approach towards modeling preferences, which is instead of thinking about max entropy, this paper by Vivek Farias and co-authors, they looked at sparsest distribution over permutation that explains the data. Okay. And they showed that in some settings they can estimate such a model, but the assortment problem actually becomes independence at heart for sparse distribution. In fact,
but it's a very funny model. Say.
In fact, that is one of the critiques that we had, that if you have support over these sparse distributions, let's say you have support over a permutation 1, 2, 3, 4 and 4, 2, 3, 1. It's unlikely that there's no probability of 2, 1, 3, 4. So a more smooth distribution is more natural and in fact more robust as well. So that was another motivation to consider a smooth model, which is Mallows is an instance of that. So in fact, we just to test this intuition, what we did was we took this sushi data set which has ranking data. So we only looked at the small data set which was ranking 10 types of sushi, and this was the full data set. It was small, 5,000 full rankings of 10 types of sushi. So we looked at the empirical sparse model, which is 1,500 rankings for our training model, and we fit a mixture of Mallows model on that, and we compared the out of sample log likelihood on choices between the empirical and the mixture of Mallows, and this is what we got. So in mixture of 30 Mallows, we were able to match empirical with 1,500 rankings. So we are basically maintaining only 30 ranks as opposed to 1,500 empirical ranks. Okay. So I've been talking about Mallows. So let me define what the Mallows model is. So this is a distribution over permutation model, which is given by a mode permutation sigma naught and a scale parameter theta, or concentration parameter theta, which says that probability of any permutation sigma decays exponentially in the edit distance from sigma naught. Okay. So to specify this model, I just need to specify you the mode permutation sigma naught and this concentration parameter theta. That completely specifies the distribution. Okay. Now finding the normalization coefficient is not easy. Okay. Now you can say that even how do you even compute a probability of a given permutation? So that's not a straightforward question, but and that's one of the questions that we answer in this work. In particular, what we want to first of all do is, even before we go to assortment optimization, we want to look at the choice probability question. So if I give you a subset, what is the probability that you will select an option J? Okay. Even simulation, for instance, is not really straightforward. Okay, so this work, let me let me give you the punchline of our contribution. So we have an efficient algorithm which can compute these choice probabilities exactly. Okay. In fact, the algorithm is just solving a system of linear equations, a compact system of linear equations. Okay. Now, based on that algorithm, we can formulate the assortment optimization problem as a compact mixed integer program with reasonable computational performance. Okay. And also, we can give a pitas for the assortment optimization problem over the mixture model under an additional assumption that I'll get to later. Okay.
So the first problem is just given the model computing.
Given the S.
So just the normalization constant, basically.
More than that. So I want to. So given S, this is the probability. The second line. So it's going to be the sum over all permutations, where J was the first among S. Okay. So that could be exponential.
So currently, for what class of models can you have efficient algorithms for computing these choice probabilities?
So most models that have been considered in literature have closed form expression. Multinomial logit is a very simple closed form. Mixture of multinomial logit is just a direct mixture. Last year I talked about
mixture of multinomial. You also said it models almost any distribution over permutations.
But the number of segments can be very high. Okay. So that's an existential result by McFadden and Train. McFadden was the first to introduce the multinomial logit in this.
Okay, that's what I wanted to reconcile.
Yes.
With. Okay.
So the number of segments could be arbitrarily large. So that's an existential result.
Okay. That makes sense.
Okay. Yes. Okay. So let me first. Okay. So let me first tell you an interesting property about the Mallows model. So Mallows model is actually the distribution is a stationary distribution of the following Markov chain. Okay. It's a Markov chain over where each permutation is a state, and the transition and you have a transition between adjacent permutations, and by adjacent I mean that are one adjacent swap away. And the probability of the transition probability is if you are moving away from the mode, the probability is e to power minus theta. And if you are moving towards mode, it's 1. Okay. And appropriate normalization. Here the normalization can be just 1 over n. Alpha can be 1 over n. That's it. Yeah.
Sorry, alpha doesn't correspond to anything in the Mallows model?
No. So actually, I can put down alpha equals 1 over n because there are only n edges. There are only n neighbors, right? For every permutation, you can only have n adjacent swaps. So there are only n neighbors. If you're moving away, the probability if you're moving away from sigma naught in the distance, the probability is e power minus theta over n. If you're moving towards sigma naught,
smaller number would also give the same stationary distribution.
Sorry?
Any smaller alpha would also give the same stationary
as long as
distribution.
they add up to 1. The transition properties add up to 1, right? You need to normalize it so that these are transition.
So 1 over n doesn't add up to 1, right?
So I'll add the remaining to a self loop.
Oh, okay.
Sorry, what's and you need also sigma and sigma j to be adjacent, right?
Yes.
Because otherwise, so you need okay.
Yes.
Because right now in the formula it doesn't imply adjacent.
Oh,
it does because it's plus or minus 1 distance.
Yeah. No, but it could like have like, for example.
Oh, I see. Okay. Yeah. So this
directions.
is yeah. Sure. So they need to be adjacent.
Like you go like 2 units to the right, 3 units to left. You go from here to here.
Yeah, it's not. I'm cheating on this slide. Like I'm saving some work on some words.
Oh, yes, right.
They need to be adjacent. And
I see. You mean they are on opposite sides of
sigma
naught.
Okay.
Zero,
and then, but the distance to 0 decreases, but.
Okay, so so once I have a Markov chain, then we can use these well-known MCMC techniques to at least do approximate sampling. Okay? And at least we have a way to compute choice probabilities. Okay? But I want to note that this was an exponential decay model. So for some products, this probability can be exponentially small. But they still may be important because their revenue, their price may be double exponential. So this can lead to many samples to compute to get to that exponentially small probability. So it would be nice to get an alternate algorithm which is more efficient than MCMC to compute these choice probabilities. Fortunately, this can be done, and we used an exact sampling method for getting an exact sample of Mallows distribution, and this is work by Liu and Boutillier in 2012, who give the following algorithm to get an exact sample of permutation from this model. The algorithm is the following. So let's say the mode is 1 to n. Okay, so you start with placing 1. Okay? Now 2 can be placed either to the right of 1 or to the left. So I place 2 to let's say preferences decrease in going right. So it can be 2 can appear to the right with probability 1 over 1 plus e power minus theta, and to the left with probability e power minus theta over 1 plus e power minus theta. Okay? Because if I place it to the right, there's no disagreement with the mode. If I place it to the left, there is one disagreement with the mode. Okay? So I would do that. Now let's say I place it to the right. Now for 3, I have 3 options. I could place it here, here, or here. And I just do it geometrically with geometrically decreasing probability. I place it to the right, to the most rightmost position with this, with proportional to 1, proportional to e power minus theta, and proportional to e power minus 2.
Because you can sample the substrings
exactly.
Doing that
exactly. So this is not our work. This was already known in this prior work of Liu and Boutillier, that we can get an exact sample and much more efficiently than doing MCMC on the exponential state Markov chain. Yes. Now, but this has further nice properties that I can actually use this procedure in a dynamic program setting to compute the choice probabilities. Okay, and in particular, what we can say is
you don't know the starting point of it. Like that was an algorithm that can sample if you know that the theta, like
sigma 0.
Theta.
I know sigma 0 and theta. Yes.
You know sigma 0, but then when you want to learn, you don't know.
Yes. So then
you have to learn sigma 0 as well, no?
Yes. Okay. So in the learning, so in that smoothing, mixture where I compared the out of sample log likelihood, we had a heuristic, EM heuristic to learn. So solving the log likelihood is not a concave.
So the problem that you're trying to solve is
assortment optimization for a given model.
For a given model where you know sigma 0 and theta.
Yes.
Okay. But then,
yes. So for learning, we need, as in we resort to EM.
okay.
Yeah. Okay. So now we can formulate this computing choice probabilities as the following dynamic program. So I'll introduce the following state, pi isk, which is what is the probability of selecting I at position S when you only have inserted 1 to k.
What do you mean position S?
Position S in your list.
Oh, no,
So there are k positions.
So okay, S and S are different things. So there's
Oh
a
yeah,
big
yeah.
S.
There's a little S. Sorry.
So there is a position.
Okay.
So what's the different position and step? What's the, sorry.
Oh, so after the kth step, meaning after I have inserted in my insertion procedure, I've inserted k items.
Okay.
After I've inserted k items, what is the, so right now you have a random sample from 1 to k. What is the probability that some item I is chosen at the sth position in this random sample?
Okay, and I is also done between 1 and k.
Yes.
Yeah. Okay, everything is between 1
Everything
and k.
is between 1 and k. Yes. Okay. Okay. So the formula. So just to illustrate it by example. So let's say my offer set is 1, 4, and 2. These are my options that are available. And I want to compute this probability. What is the probability that 1 appears at position 2 in the random list 1 to 6? Okay. So suppose I have the probability that it appears at position 2 in the random list from 1 to 5. Now 6 can be in. So for 1 to keep appearing at position 2, 6 must either be inserted after 1. Right? If 6 inserts here, I'm fine, and I know exactly what the probability of inserting 6 is in those locations. Okay? Or 1 actually appeared in position 1 and 6 goes before. These are the only 2 cases when that 1 can keep appearing at position 2 in the random list from 1 to 6. And I know the probability of these blue dots, and I know the probability of this green square, so I can just combine. Now, product 6 is a new product which I don't know, which I didn't have from before. So, what is the probability of choosing product 6 at position 2 in the random list from 1 to 6? That's going to be that all products that are in my offer set are in position 2 or higher, because if something is at position 1, then I cannot have 6 at position 2. Okay? So and 6 should be inserted at position 2. Okay, so this is the only case. So now this sets up my system of equations, which is pi I s k plus 1 is probability that the k plus 1 goes at the end times pi I s k, or if k plus 1 goes before, then I should have appeared at s minus 1, and k plus 1 should not be in the assortment. Okay. And similarly, you can write the equation for this. So this is a system of equations that I can write, and then the choice probability of I is just sum of all the positions of pi ISN. Okay. So that's a simple system of equations that will give you exact choice probabilities, and these are order n cube. These are order n cube variables. Now, if you have a mixture of Mallows model with L mixtures, this is order n cube L.
N is the size of your offer set, right?
N is the size of all the items.
What is pi of I here?
Oh, pi of I is pi of IS, capital S. Choice probability of I, given the assortment. So here the assortment
would be just pi I of I and 1 and n?
No. So I can be chosen at any position, right?
But we only pick it if it's the first one, isn't it?
If it's the first one, then everything is offered. But here only, let's say 1, 4, and 2 are offered. So 1 can be picked here, here, here. There are 3 positions where you can actually make a selection.
I'm not sure I understand.
Sort of I think the way they use it, you order all elements, the ones that are in the offer set and the ones that are not in the offer set. And for the item to be picked up in position J, it must be the case that it must incorporate the probability that all the elements before J are not in the offer set.
So therefore,
That's
you can
the-
go to a deeper position. So if there are n elements and you only offer n by 2, so you can go up to n by 2 position, right? Your choice can be.
But the elements themselves matter, right? Which elements are in the set and which elements are not in the set.
Yes.
How does that figure in that formulation?
Okay. So this is xk plus 1. So either k plus first is inserted to the right, then it doesn't matter it's offered or not. If it's inserted in the front, then it should not be offered.
I see. So pi of I S K is actually the probability when only the set S is offered,
Yes.
I being the S one within the set S or overall?
No. So phi ISK is probability that I is chosen in position S
Okay.
from 1 to k.
So the insertion procedure goes in
So-
steps.
So
After k steps of the insertion procedure, you want I to be in the S position.
Right. I'm wondering where this sets S figures in this.
maybe,
definition.
I think the confusion is, so this little s and capital, so capital S is the set and little s is the index of where in the rank.
So is this pi I S K, does it depend on capital S or not?
Yes, it depends. So it will be 0, for instance, if I is not in S.
So the keyword I think is chosen. So chosen means like that if you take the intersection of S and if you look at the ranking
On 1 to K?
And
Yeah.
1 to k.
and 1 to K, that would be the I should be the first element appearing both in S and K. Correct.
I being the S element appearing in both.
Yeah,
1 to K
exactly.
and S.
I is the S element in that sequence.
is the
and
Sth
appears
element.
in big S.
Appearing in both S
And 1 to k.
1 to K. So then why is pi of I summation and not just pi of I and 1 and
Because so when you choose, you may end up choosing at any position in the list. You will choose the first item among the set, but that first item could appear at the top of the list, could be the second, could be the third. Let's say there are 10 options and I only give you 3 options. I only offer you 3. Then in your list, your top choice among the 3 options can appear at 1, 2, up to 7th or up to 8th position.
okay, I don't want to hold up.
So I think it may help if you put an and after chosen. Because the first way I read this, it was as if chosen doesn't mean anything.
Oh, I see. So chosen meaning is you just look at your preferences, S intersection 1 to K.
Yeah.
Which one do
I
you-
know.
which
I'm
one do
just,
you select?
Just saying, just a suggestion for your updating your
I
slides.
see. Sure. Thanks. Yeah. Okay. So with this linear system, you can compute the choice probabilities exactly, and the running time for this particular algorithm is n cube L. We can do this more efficiently. We can shave off a factor n and get a n square log n using a different representation of this linear system using Fourier transform and implementing a fast Fourier transform. Okay. So now to the assortment problem. Okay. Just recall the assortment problem is, let's say, finding the subset of options that maximizes this expected revenue. Okay. Now, I want to just go back to this linear system of equations that define my choice probabilities. This linear system has these variables which are saying, or has these xk's which are saying whether this k plus first item is in the assortment or not. So that I have a math program already there, which is if I think of these xk plus 1 as variables. So I can first of all off the bat write down a mixed integer formulation. It's a non-linear formulation because my variables are pi's and x's. So both x and pi are my variables, which makes it non-linear or bilinear. But I can linearize these products of xk and pi I by these set of introducing new variables and just adding these constraints. Okay, so right away I can get a mixed integer program, mixed integer linear program with order n cube variables to solve the assortment problem. Okay.
Sorry, you're saying without forbidden. You have this okay x and pi and you linearize these things, but what's the issue? You need how to represent the top, the maximum.
How do I represent the? No,
I mean the objective function is not bilinear.
The objective function is linear. Prices are fixed, and pi was linear system, right? Pi is the objective function is linear, but constraints were non-linear because one, you have a product of 1 minus xk times pi, and you have a product of xk times pi. So both x and pi are variable.
Okay, but once you introduce this y's,
yes,
then you need to replace the pi's by a y in the top.
So I would replace xk times pi with this this product by this variable, and I would add in these constraints. So this is a standard linearization of a bilinear term, but I'm still constraining xk to be 0 or 1.
Ah, okay, sorry. That's
okay.
Fine.
So that's why it's an integer program. So
yeah, no, that makes complete sense.
Okay, so just to think of it, we had a distribution which had a support of n factorial, and a naive way of formulating the problem would have exponentially many variables. So here we get a compact mixed integer program. It's not polytime, but that's a start. So furthermore, instead of n cube, we can get 2n square also. Okay. So the first thing we did was we tested out this formulation, and we saw that actually it scales reasonable for a size 40 problem. That's a huge problem in the permutation space. Okay. And for instance, if the parameter is 0.85, it solves under roughly 2 minutes. Okay. But you would notice that there are some outliers. Okay, so this is not really scalable. I can't claim this is just you use it as a black box. Okay, but then we digged a bit deeper and we saw what is happening in the solver. So I have 3 instances of that hard parameter setting, n equals 40 and the parameter being 0.9. So I have the duality gap that the solver obtained. So within very quickly, the solver was able to find a good solution. Okay? The rest of the time was spent in closing that duality gap, which just means that our relaxation is very bad. And that actually, this is the part this is the part that is actually quite bad. This relaxation. Relaxing this bilinear product using these 3 constraints, that is very bad. And there we have some ideas that
is that actually relaxation, or I thought that's an exact formulation.
If you have xk being 0 or 1, okay. But the solver will be solving relaxation and doing a branch and cut. Okay, so if the relaxation is bad, which is the case as confirmed by these duality gaps, the time taken to close the duality gap. Okay. So we have some ideas where to close this, to have a tighter formulation that we are exploring. But another question is, what about a polytime algorithm? Can we say something? Can we get a near optimal algorithm that runs in polynomial time? Okay. And we have some good news on that end as well. But we need an assumption. So no assumption is not possible because I said the assortment optimization over sparse is independent set hard. Therefore, mixture of Mallows will capture the sparse also with appropriate scale or concentration factors, right?
So I kind of missed it from your table. It was doing poorly at 0.9 at high concentration.
At low concentration.
Could you see the table again?
So if you make this parameter 0.99, then it's a uniform, or 0.999, then it's a uniform, then the formulation should run fast. So if the parameter is very low, then also it's okay. There's some range where it actually becomes hard.
So I guess maybe what Sebastian is, the way I understand what Sebastian requires that there should be the easy setup, right?
So the easy setup would be uniform, for instance, or like very concentrated.
Because theta goes to 1, theta 1 should be
that is trivial. Yeah.
But then you should have like a good approximation to the grade.
So it's not monotone.
Just using the uniform solution should be a good approximation, right?
So that depends on the prices, the P's.
Or
if the P's are really,
okay.
If the P's are arbitrarily high and arbitrarily low, then uniform may not be as good. Mm-hmm. But yes, in a reasonable, let's say all P's are between 1 and 2. That would be a good setting. Okay. So go to a near optimal algorithm. In fact, we can give a p-task for assortment optimization under mixture of Mallows model, but under an assumption. Okay. The assumption that we need is, let's think about the single Mallows model and think about the preference of users for products which are less preferred to the no purchase, to the null option. So the assumption we need is users are indifferent between options that are less preferred to the no purchase option in the mode.
What do you mean by indifferent?
Yes, so let me find. So let's say our mode for Mallows distribution is the following: 1 to L, then you have null, and then you have L plus 1 to N. Okay, let's say this was our mode. Then I'm saying the real distribution is a uniform mixture of these n minus, it should be n minus L factorial modes, where the first L are 1 to L, but L plus 1 to N appear in a random order. That would make users indifferent between L plus 1 to N, on average.
I found this a bit strange because they could pick any product and make it the no purchase. They could pick product L and say that the price of product L is epsilon.
Okay.
So epsilon now acts as the no purchase. So the no purchase is, I don't see it as being a special product.
So nobody, yeah, in the Mallows model, yes, it was not a special product, but in the application, no purchase is always going to stick in the assortment. So it is a special.
That's actually more this question. Okay,
yes.
That's the reason no purchase always in the assortment. There's a difference between.
Yes.
Okay. Yes. I only could remove from the assortment. No purchase you cannot.
No purchase you cannot. Yes. Okay. So under this setting, we can give a p-task. In fact, an algorithm which has running time polynomial in n to the 1 over epsilon, and k if k is the number of mixtures.
Okay. What's the quantity that you discretize to n over epsilon? You have to.
Yeah. So I'm coming to that. In fact, the algorithm is very simple. The algorithm depends on the following probabilistic property about the model, that if you look at any two products, I and j, such that I was better than j in the mode, I was more preferred to j in the mode, then probability that I remains preferable to j is at least half. This is an easy argument for Mallows. In fact, you can prove this for more general class of models arising out of Markov chain, stationary distribution over the Markov chain. In fact, we can prove a more general property, which is, let's pick any m options, I1, I2, Im, and this is the order, this is the restricted order in the mode. then probability that mth option becomes the best among these is at most 1 over n. Okay. So we can prove this by a coupling argument on a sample path basis. So look at all sample paths where IM is better. We can couple them with other sample paths where one of the other option is better, and therefore we can partition the sample paths into m buckets and show that this sample paths or these samples will have the least probability. Okay. So these properties allow us to prove the following structural result about a near optimal solution, which is among these options, the users were indifferent. So just pick the top K prices, some top most expensive products from this. Okay. Among these products, there is a near optimal solution where you only need to pick at most 1 over epsilon items. Okay. In fact, the idea is the following, that let's say S star is the optimal solution. You look at the intersection with these items and pick the top 1 over epsilon priced items from these guys. Probability that the null becomes better then the top 1 over epsilon is only epsilon.
You just enumerate over this choice.
And then you enumerate over these choice. And since you are enumerating, and this part was simple, you were only picking the top few, you can handle a wide variety of budget constraints. Okay. Okay. So this gives us the algorithm, and you can get a 1 minus epsilon approximation. Again, this is probably not practical in the setting, in the sense that you n to the 1 over epsilon. So we didn't even attempt to compare to our MIP, but it at least gives us a theoretical footing that this model may be easy under at least some assumptions. And what we want to push upon is the structural results about the probabilistic claims and properties of the Mallows model, and also the ideas that we needed to develop the mixed integer programming formulation to push towards an exact algorithm for Mallows model. That's something that we don't know, doesn't exist. So we don't have any hardness result about the Mallows model. And my conjecture is that we should be able to get an exact algorithm. Okay. So I want to go back to something that I started with, the relation, and this is where we actually started this journey of thinking about mixture of Mallows, was a non-parametric approach and the max entropy distribution over permutations. So suppose you're given this data, which is pairwise comparisons of some of the problems. Okay, fraction of people who prefer I to J. Now you can write this convex program to find the max entropy distribution. P sigma is probability over permutation sigma, and you're trying to maximize the entropy subject to consistency with data. Okay. It's well known that the solution to this is an exponential family of this form. Okay. So basically, this can be represented as a stationary distribution over the Markov chain with appropriate transition probabilities and edges only between adjacent permutations, meaning that are one adjacent swap away. Okay, and this is exactly, this is a very Mallows is a special case of this max entropy distribution over pairwise comparison. Okay, and that was the point that I wanted to bring out earlier. So our hope is, at this point, I don't have any further intuition about max entropy, but the hope is that under some assumptions, we can use these ideas to build upon and develop a framework and algorithm for max entropy. So given data, we can find a distribution. So we can compute these lambda ijs. We can sample from them. So we can compute choice probabilities using MCMC again. But MCMC doesn't give anything to, doesn't give us any framework to build towards an assortment optimization question. So that's something that.
So where does this result come from? The P sigma result.
Oh, this one is just writing the Lagrangian and taking KKT.
I see. And are these actually easy to compute?
So these are not easy, like these are not straightforward to compute because you will have exponentially many constraints in the dual. So I can't compute P sigma, but I would just want to compute lambda ijs.
Right.
So the number of variables is small, but the constraints are exponentially many. So I need an ellipsoid. I need to develop an ellipsoid that's specific for this application, and we can do that for this particular.
So that's known. So you.
That is so. So there is this. There is a result by Nishit Vishnoi and Mohit Singh that appeared, I think, in Stock 2-3 years ago, who where they show that if you can sample, if you can give me a sampler, you can optimize. And they were using that to compute max entropy distributions.
In the same model?
Not in this model. They were no. They were looking at max entropy distribution over trees and with some marginals in other settings. But we need that framework, and we were able to design a sampler for our dual problem to solve the separation problem over our dual. Okay.
I'm actually curious what when QIJ is feasible. It should be like a nice question.
Yeah, actually, that's. But the sampler should answer that. So ellipsoid will at the end say infeasible, right?
That's true. Yeah, that's true.
There should be easier answers to
be
that.
But there should be more structural answers to
There
that.
should be a structural answer to that.
Basically, you want to characterize the polytope. That's the convex combination of all the permutations, right?
Yeah, there should be something.
That is Markov environment. That is just Markov environment. But that's not what this is.
Then that's it, right? Is that the Markov environment polytope? Yeah, that should be that. I mean, there's a projection of the Markov environment.
It will be the projection of the Markov, and projection computation is not easy. So I can write the Markov environment polytope, that's fine, but projecting onto the QIJs is not.
Is that the Markov environment? Actually, no, I'm not sure anymore. For every permutation, you get like. I guess for every permutation, you get an n-square vector of that type.
No, so you can get, so there's a more compact representation also with n log n permutahedron. This is the result by Michel Gomez. So I want to find a convex hull of permutations of 1 to n, write the description. So he has a compact representation in the extended dimension with n log n variables and order n log n constraints.
So what is your question though? For you're curious about what kind of QIJ?
I'm curious about if you give a QIJ matrix, if you can check if there is a set of permutations that generate that QIJ matrix or not. Pretty much now I think
I'm guessing it's not possible because that would mean that you can, like, assuming that you can actually characterize it with like linear. If you can characterize the polytope, then you'll be able to optimize various things on it.
Oh, it's wrong, but you probably can optimize because this is sort of a reciprocal optimizing things. I mean, that's just for entropy distribution, but it could, because it might, what it doesn't, every permutation be a QIJ matrix of that type. Like just
for example, the feedback arc set problem, right? So you want to order the vertices of a graph. That problem is basically finding a permutation of nodes that maximizes some linear objective function. Right?
Linear on the pairwise comparisons.
Linear on the pairwise comparison, exactly. So if we can characterize the polytope, we can just optimize over this one.
But it could be true that to return me
So maybe
an integral solution, which is a little. I don't know. We're saying that an integral solution should be easier.
No, I'm saying that. So you do need an integral solution, but if the polytope, and your question is to characterize the polytope, that's the convex combination of all the integral solutions, right? If you could do that, if you could characterize it with a separation oracle, then you could just optimize over that polytope, and the optimal by definition would be an integer.
I see. That's a good point. Yeah. So the way I was thinking that the interest, so the vertices of the matrix like this, right? A bunch of ones here and a bunch of zeros off the diagonal. You could permute all.
Well, what is that? So this is easy. This is fine, right?
This is one vertex of the
This is one vertex of that.
Yeah. Now I want to say now you can permute all those guys and you get all the matrices and you say even a matrix is it.
Can you express it as a convex combination of
this matrices? But you're right, so you're saying that if we can do that, the feedback are such as can express on those variables, xi, j. Yeah, right, just need to solidify it smaller than j.
I think that implies that it's fine.
Yeah.
I agree.
That's a good, yeah, I think it's Thanks, it's nice.
That's why
It's a pretty, it's a good description.
So yeah, just to conclude that, so we started out with our goal towards a non-parametric approach, which remains a goal. But in the process, we were able to look at a smooth distribution over permutations model, which I think is more natural and more robust, and develop algorithms for efficient choice probability computation and using that betas and also computationally practical algorithm. I still think that this is possible. Exact assortment optimization over Mallows. Mixture of Mallows would need some assumptions. We cannot do it. It is independence at heart. Even mixture of two Mallows might be NP hard, but single Mallows might be doable. So that's something that we are still trying to push. But one other thing that I want to mention and connect to the talk that I gave last year, I think Balu, you were there. I think you were there as well. Is this new class of model where choice probability is a linear system of equations, and we don't know the parameters of that linear system. So instead of going through the other route of recovering the utility model that defines the preferences, which is what multinomial logic and mixture of multinomial logic stream of literature has been doing. If you think about just choice probability as a linear system in some dimension, here the dimension was extended dimension of n cube, so fix the extended dimension, it's a linear system in that dimension, try to learn the parameters of that linear system. So we can we can map it to a lot of work that is out there in learning linear system out of observations which are solutions of that linear system. Okay. And that also maps to a model, another model that I presented, which was Markov chain over product space defining preferences. So you walk in a Markov chain over the state space of products that defines your preference, and that is also a linear system of equations. Okay. So thank you. This was based on these two papers with my students and co-authors, both of which are available at my. Thank you.
Thank you.
Thank you.